I am Isaac Newton, standing now in the Grand Hall of the Royal Society. The solemn and somewhat cold atmosphere seeps into my being. Through the display case, I see the familiar manuscripts, filled with my painstaking calculations and profound insights, the crystallization of my lifelong pursuit of knowledge. These are my works, such as Philosophy Naturalized Principia Mathematica. Here they rest, in this hall of scientific glory, labeled in the language of modern academia, yet still carrying the weight of centuries of scientific exploration. I reach out my hand, as if trying to touch the pages that once held the spark of my scientific inspiration. In my era, the age of enlightenment was just dawning. The scientific world was in a state of flux, with the old Ptolemaic system gradually being challenged by the heliocentric model proposed by Copernicus. The concept of natural philosophy was evolving, and the pursuit of empirical evidence and mathematical precision was becoming the norm. I was driven by an insatiable curiosity to understand the fundamental laws of nature. I spent countless hours in my study, poring over books, conducting experiments, and making observations. One of the most significant moments in my scientific career was when I witnessed an apple fall from a tree. This simple event led me to ponder the force that governed the motion of objects on Earth and in the heavens. I began to develop the theory of universal gravitation, which states that every particle attracts every other particle in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This was a revolutionary idea at the time, as it unified the celestial and terrestrial mechanics, breaking the long-held dichotomy between the perfect motion of the heavens and the imperfect motion on Earth. In the process of formulating my laws of motion, I also delved deep into the field of calculus. Calculus, which I independently developed, alongside Leibniz, became a powerful tool for describing the changing rates of physical quantities. It allowed me to analyze the motion of objects in a more precise and comprehensive way, laying the foundation for modern physics and engineering. With calculus, I could calculate the orbits of planets, the trajectories of projectiles, and the behavior of fluids. My work was not without its challenges. The scientific community was initially skeptical of my radical ideas. There were debates and controversies, but I was steadfast in my belief in the power of reason and evidence. I knew that my theories were based on rigorous mathematical proofs and empirical observations, and I was determined to defend them. Now, as I stand here in this hall, I see young scientists looking at my works with awe and admiration. They study my equations, trying to understand the principles that have shaped the modern scientific world. But there is also a sense of sadness within me. My manuscripts, which once held the secrets of the universe, are now just artifacts in a museum. The scientific world has moved on, with new theories and discoveries constantly emerging. The progress of science is like a river, constantly flowing and changing. My contributions, though significant, are just a part of this long-running scientific narrative. I am reminded of the words of Robert Hooke, with whom I had a complex relationship. The scientific community is a collective endeavor, and each generation builds on the work of the previous one. My spirit is both proud and a bit melancholic. I turn away from the display case and walk towards the exit of the Royal Society. Behind me, my works remain a testament to the power of human curiosity and the pursuit of knowledge. In the end, science is an unending journey, and my place in it is but a chapter in the grand story of human understanding of the universe.